This is All Things ANSYS, a podcast from the technical support staff at PADT. Episode 110, we talk with Tom Chadwick on how companies use a wide range of ANSYS products to increase efficiency and reduce pollution. Then, take a look at news and events in the world of ANSYS. I want to welcome everybody to the first week of May 2022. My name's Eric Miller. I'm one of the owners here at PADT and your host for these podcasts. For many of you, spring is in full force. Our listeners from south of the equator are starting to see the signs of fall. Here in Phoenix, it's just starting to get hot. So we're ready for it. We're used to it. This is episode 110. It's another milestone, a nice round number there. We're quickly approaching 35,000 downloads at 34,800 right now. That's the official count, not counting ones that get downloaded elsewhere. And that is up to 319 downloads per episode, which is an increase. We were stuck for a long time at 310 to 315, so we're slowly inching our way up, but with 110 episodes, it's going to take a while to get that number up. So please keep spreading the word, and don't forget to subscribe to the podcast. So uncertainty and problems are still plaguing the world. I don't want to dismiss them before we get started. The pandemic, war in Ukraine, inflation, a dozen other things. And I also wanted to send in a special bit of sympathy for our listeners in India. We have quite a few who are seeing an unprecedented early heat wave there on the subcontinent. So as always, our thoughts go out to everyone facing difficult times. We hope you find our podcast a small oasis where we can talk about how to use technology to make the world a better place. And speaking of making the world a better place, one way we can use simulation to help is to use the tools we know and love to increase efficiency and decrease emissions across products and industries. Optimizing designs, improving remediation and removal systems, experimenting with new processes and methods through virtual prototyping. All these things are things we can do with the ANSYS toolset. And today we've got Tom Chadwick, one of PADT's CFD engineers, and he's going to share some industry best practices and help us understand what we can do, what we can get done using ANSYS tools in this very important area. I want to welcome everybody, and especially Tom Chadwick, who's joining us today to discuss a really important topic. And it's about ANSYS, but it's about how we can use ANSYS to reduce various kinds of pollution. And it's an interesting topic because it's a great application of simulation tools, and we'll talk about that. But it's also, as we look at trying to mitigate some of the stuff that we're putting into the air and the water and the ground, how can we as simulation people help reduce that, and how can we help our employers meet their goals to do reduction and mitigation? And simulation is a really important tool in that. So Tom, I want to thank you for joining us.
Hello.
And so Tom, you just recently did a seminar on this, or you're going to do a webinar on this?
I just did a webinar a couple of days ago.
Excellent. So we'll definitely mention after the recording where people can find that to get more details, and actually instead of trying to visualize what Tom's talking about, actually see pictures of it. And before we started recording, I caught up with Tom a little bit about what we're going to talk about, and you had mentioned that there's really you can put this kind of work into four categories: tuning combustion, emissions reduction, exhaust gas quality control, and then effluent water quality. So I think the one that I'm most familiar with, because I'm a turbo machinery guy, is the first one. Why don't you share with us the kind of a high level of what ANSYS has available to help people tune that combustion process of producing energy?
Okay, so the tuning combustion process, the big issues are that anytime you burn fuels, there are things that come out of the combustion process that are harmful. There's various forms of NOx, there's carbon monoxide emissions, as well as soot and other, combustion products that can be harmful. Mm-hmm. And the idea is that if you can properly control the combustion process, you can minimize some of these harmful products. And part of the problem is that it's a balancing act because efforts to reduce NOx emissions can elevate carbon monoxide emissions and vice versa. So if you have to kind of strike a balance between temperature and duration, things like that, to balance out what you get out of the combustion process.
Okay. And so what tools do we use in ANSYS to help us balance that whole thing?
So basically the Chemkin tools can be used to define the species for the combustion process. And let's see, here's the list. Model Fuel Library, which is one of the products that comes out of Chemkin, has detailed chemistry for a wide range of fuels.
Great.
So you can accurately predict what's coming out of the combustion process. You can also use the other Chemkin products, Chemkin Pro and Chemkin CFD, to do, Chemkin Pro is for 0D and 1D combustion modeling. So you can kind of control your fuel mixture and the time of reactions and do a very quick analysis and, do trade studies with Chemkin Pro quickly to get a good idea of where you're starting from. And then Chemkin CFD and the ANSYS CFD products can be used to do detailed 3D, both steady state and transient combustion modeling.
And are we talking like reducing emissions by 2%, or if you do this right, you can get some big number reduction in, say, NOx, or you can't really reduce the CO2, right? But on the NOx and the other nasty stuff.
Yeah, let me see. The big thing is that we're talking about removing CO2 emissions by 50%.
Oh, wow. Okay.
40% reduction in greenhouse gas emissions.
Okay. So big numbers. This is not tweaking your efficiency by a little bit. You're really optimizing the reaction to get rid of the molecules you're trying to.
Right. Yeah. It's all being driven by government regulations. They're requiring that these older, coal-fired plants, combustion tools, gas turbines are all have to be upgraded to meet these new requirements.
Okay. Really cool.
Yeah.
Yeah. So are we using Fluent or CFX on the CFD side for this, or both?
Fluent is primarily the tool that is connected with the Chemkin processes. CFX has some chemistry capability in it as well, but their focus has been to integrate Chemkin with Fluent.
Okay. And this is applicable for folks working on smaller devices with the combustion, not necessarily the big guys. Many of our listeners work for the people, doing the big power plants or the big gas turbines or the big coal fire stuff. But this could be a small device too, right? That you can get.
Yeah, any device that employs combustion. You need to be concerned about it because all combustion processes have these kind of outputs.
Yeah, I'm always reminded of concrete. Some of my greener friends always remind me, greener engineering friends, that know what's really going on, that concrete's one of the burners for concrete manufacturing are one of the sources of greenhouse gases and other chemicals as well. So,
right.
Yeah, so that's another good application. That's really cool. Okay.
Yep.
So that's the one that I think most people would have thought of when they read the title of this one. At least I did. So let's move on to the next one, which is emissions reduction. So what's that about?
Emissions reduction is basically it's complementary to the first one because,
Right.
as I said, any combustion process, by the nature of combustion, because you're dealing with high temperatures, you're going to create NOx, you're going to create carbon monoxide. Emissions reduction technologies are things that you put on after the fact. You've produced the NOx from the combustion process. Now you have to add something in at the tail end of your combustion process to prevent that stuff from getting out into the atmosphere.
Okay.
And those are things like ammonia injection, where they inject liquid ammonia into the exhaust gas stream, and the liquid ammonia reacts with it and helps reduce the levels of those harmful emissions. And other things, catalytic beds, things like that. So like your catalytic converter in your car is a perfect example.
If it wasn't cut off, like, those of you, I don't know if you knew this, but those of you who know PADT know we've got these old Priuses that are company cars that we use to drive around town. And we had 3 catalytic converters stolen from them last weekend. So,
jeez. Yeah,
that's a little off topic. Sorry, folks, but I couldn't help but think about it when he said catalytic converter. Hopefully, maybe the answer is hopefully design them with less precious material in them, so that and be more efficient with less platinum and other stuff, so that they aren't such a theft target. Yeah.
Well, and the other problem is that by the nature of the way they're designed, they're basically this fine mesh or corrugated material. And since you're flowing hot gases over them, over basically metal, it expands and contracts as you go through that drive process. And so over time, catalytic systems weaken because of those thermal stresses.
Okay.
And so part of what ANSYS provides is the ability to run an integrated analysis. So you run your CFD to determine what the temperatures are in your catalytic bed or device. Then you take that information, you feed it into a ANSYS mechanical and do a thermal analysis to determine how much the material grows or wants to grow due to the thermal changes. And then you take those thermal growth numbers and then feed it into a stress calculation and determine how much stress you're doing. And you run that over and over again and do a cycle analysis to determine what stress you're doing to the catalytic bed.
Okay. I didn't think about that, but that's really important. That thermal stress fatigue is an important part of it. And then I assume that it does like the multi-species part in the CFD and turbulence. Right. I'm guessing, as usual, you either don't want turbulence or do want turbulence. I don't know which, and you model that as well.
You need to have turbulence because I mean, obviously, all these processes are involved in passing the gases over a surface or mixing the ammonia with it. So you've got a turbulent interaction, turbulent mixing. And so you have to have turbulence models involved with it.
Very cool. Okay. And so this will help you not just optimize your process and it also helps you deal with the robustness of the system with this thermal issues, which is great.
Right.
Great to know.
So it's taking into account not only that, but the life of the product. So you've got to be concerned with how often you're going to have to replace these things.
Cool. Very cool. Excellent. What about the next one? Which is, you got me thinking about that now, and so I got to change gears here. so these are all kind of related, but exhaust gas quality control. How is that different than the emissions reduction or controlling the combustion process, and then what do we do in ANSYS to deal with that?
Well, exhaust gas quality control has more to do with solid particulate matter.
Okay.
So if you've
Soot
got
and stuff.
soot or
Okay.
anything else coming out of your, because this exhaust gas quality control is not just combustion processes now.
Okay. Okay.
It's anytime you've got a process where you've got solid particles
Okay.
in the flow.
Okay.
So any kind of a chemical processing or other types of processes where you might have particulate matter being created.
Okay.
And so then you need to be able to strip that out of it using things like filters or electrostatic precipitation.
Okay.
To pull all that stuff out, or using the aerodynamic process itself via something like a cyclone. So you're back to your Dyson vacuum cleaners.
Yes. I do remember with a little bit of the work I was doing mentoring in the clean tech space with startups in the clean tech space that was quite a trendy thing to do for a while, was cyclone design for basically separating stuff.
Right.
I mean, I'll be honest, there were a few companies that were just putting cyclones in because cyclones were trendy.
Right.
They never could explain to me why it was in there. They would literally say, we don't know why it works. And that was usually, they didn't make it to the next level. But so I get that from a modeling standpoint. Of course, Ant's very good at modeling that sort of thing with the particles in the flow, et cetera, et cetera. But the electrostatic caught my interest. How do we model that?
So that is actually, the electrostatic is actually a combined modeling process, because you're actually having to do couple it with an electromagnetic analysis.
Because it's got to calculate the force on the particles, yeah.
Right. So you're calculating the ion effect to the particles, and you have a surface that's positively or negatively charged, and you're attracting the particles to that to that surface, and then you've got to deal with the fact that over time that electrostatic precipitator will get a buildup on it. So you've got to go through how do you get that off once you've built it up, and how does that reduce its efficiency over time? And so basically, you're dealing with. Basically, this part of it, it's a multi-stage process. So you use a cyclone system to remove the larger particles.
Okay.
And then you use bag filters to remove, filtration systems to remove slightly smaller particles, ones that cyclone wouldn't help you extract just because they're such lightweight particles.
Okay.
And then finally, you get down to electrostatic precipitators, which are removing much smaller size particles that even a filtration system wouldn't catch all of.
Okay. And do you remember if it's Maxwell we're using to do the electrostatic part? Or is it a plug-in to the Fluent code?
I believe it's using Maxwell to do the electromagnetic.
Okay. Get that field, and then it calculates the load on the particle. Okay.
Right. Yeah.
Very cool. That's really interesting to me. What a powerful way to do it, and I think there's a lot of inputs to balance, right? It's the flow. What's the flow rate? What's that optimum position where you're getting the particles going through the field at just the right rate so they get pulled over to the side or the bottom or wherever it's going at a big enough rate, and then how do you predict when it's time to clean it as well? Yeah.
Right. And it's designing the shape of the passages to make sure that you're optimizing the exposure to the electrostatic precipitators, and making sure that your filtration systems are sufficient to catch the particles, but not so stringent that they block too much of the flow and cause too much pressure drop, which requires that you have heavier pumps to push the flow through. So
really a system optimization. Yeah.
Right. So it's a balancing act.
The cyclone up front too. So when you've got these multi-stage solutions, it really comes in handy. Very, very interesting.
Yep.
And of course, I'm instead of relating it to our stolen catalytic converters, I'm thinking of the last time that I used my wood-fired pizza oven. It does not have any of these capabilities. It's got a straight pipe coming out of the top, and
Right.
I didn't move it far enough underneath the patio, and I got soot all over the bottom of my patio. So covered. I don't know that I'm going to put a cyclone in a filter bag and an electrostatic device on the end of it, though. So for the 3 times a year, I pull it out of storage and use it. But real world there, and it's an interesting thing. And does this also play like you would probably use this on a coal fire plant as well, right? That would be the larger application.
That would be the larger application as a coal-fired plant. But like I said, basically any combustion, any process, any chemical process where you have an output to it that has particles in it.
Great.
You can use these tools to help clean that flow.
Good. And then we've been talking mostly about combustion and the results of combustion, so gases and the stuff in gases. But the last bullet point was water treatment, right? Effluents,
right?
Which we can't forget, and we want to these days. Of course, we're here in Arizona, so retreating the water and reusing it is really important to us. What's going on in the area of water treatment and effluents quality?
So
effluents. I'm sorry, effluents.
Effluents, yes. So basically, and this is modeling any kind of basically there's 3 processes. You have tanks where you're trying to separate out the larger particles, so you need to run the flow through there at a low enough velocity so that the heavier particles will settle out to the bottom. And then you have reaction tanks where maybe you mix in either other chemicals to help react with the garbage that's in the water, or you bubble air through it to try and create a froth that you can then scrape off and clean the water that way, as well as any other kind of chemical reaction that you might need to do. So if you've got a bioreactor and you need to model the mixing of the chemicals that you're putting into the water to make sure you adequately treat all the water, so you don't want to have any dead spots in your tanks, things like that.
Yeah, I'm visualizing that junior high probably field trip that everybody took to the local water treatment facility.
Yes.
And thinking about this, we've actually done a little bit of work in this area here at PADT with helping some local water treatment places. Settling tanks, I think, is the last one we did.
Yes.
And it's quite interesting, and the surprise to me was how it was not optimized. They basically just built them and they worked. And kind of hand calcy, and optimizing them could really increase their throughput was what we were finding. Yeah. Yes.
And the big thing with these systems is that, again, the scale difference in them is, I was surprised the first time I saw one of these things. It's quite massive when you're talking about a water tank that's, 20, 30 meters in diameter and, 5-10 feet deep. And then you've got these little tiny pipes that are feeding the flow into it and mixing processes, and you're dealing with transient problems, and you're dealing with mechanical issues as well, because a lot of these things have moving parts and they're quite large truss structures.
Yeah.
So there's a lot of different places where modeling can help them.
Gravity playing a much larger role than we're used to.
Yes. Gravity plays in these kinds of situations. You're dealing with very slow flow rates, and you're trying to actually slow the flow down enough so that, like I said, the particles can settle out to the bottom of the tank. And then you've got to have scrubbers that's take the stuff and scrape it off the bottom of the tank and move it towards an outlet where they can be sucked out.
Right. Right. Yeah. Complicated systems.
Yes.
I also remember getting a little bit into this. I don't know if this was covered in some of the examples, but also in the mining industry, and other, extraction processes or manufacturing processes that produce effluent. And when you treat it on site, optimizing those systems became very important.
Correct. And it's also the process. It's also similar to other processes in the mining industry as well, because very often they're, when you're treating ore, you're mixing chemicals into it to try and extract out the minerals out of the ore. But you're trying
to get it to use it rather than get rid of it. Yes.
Right. And you're trying to extract stuff out of it. And so and this kind of modeling is applicable to that
as well,
industry as well.
We were just having a discussion last night at a tech council meeting about lithium extraction, which is becoming obviously a very important need out there to increase the effectiveness and efficiency of lithium extraction. Yeah, very cool. Wow, it's got my head really thinking about a lot of different things, and I think the strong message is, that Fluent, along with CFX and some of the companion products like Chemkin and the other physics products like Mechanical or even Maxwell, which I wasn't expecting, can play an important role in hooking them together properly and setting up these runs. You could really, these are big numbers that people are getting out of these tools, it sounds like.
Right.
Yeah.
And it's, again, it's becoming increasingly a requirement now that you have to do this. It's no longer an option where, it would be nice to be green.
Yes.
The government is requiring that you do it. If you don't do it, they're going to shut you down, or it's going to, your cost benefit analysis is going to say the fines involved in not doing it make it worthwhile to do it.
Or if you're in a country with carbon trading.
Right.
Yeah. Carbon. What is it? Carbon credit, I think, trading.
Carbon credits. Yeah.
Yeah. Yeah. So this is real money.
Yes.
Yeah. The only process we didn't really talk about any of this treatment on the effluent side is evaporation and distillation. Is that something that you covered, or is that kind of considered separate?
That's separate. I mean, it's something you can do with the codes because Fluent has multi-phase capabilities. So if there are issues that you're trying to model where you've got whatever steam or whatever kinds of chemical byproducts that are coming out of it in terms of gases, that can be modeled. If you know the chemical reactions going on, and the chemical rates and the rates of reaction and things like that, you can include it in the Fluent analysis. So
because some of our we've seen that in semiconductors. Sometimes some of the semiconductor processes create water that can only the only way to get the highly toxic chemicals out of the water is through distillation. So
correct.
And what's basically pull the water out rather than the stuff out.
Right. Yeah. You either have to do a distillation process or you have to add some kind of a chemical reaction
that pulls it out,
precipitate it out. Yeah.
So that's all modelable as well. Yeah.
Right. Yeah. Any kind of a salt creation reaction you can do in Fluent.
Okay. Very cool. Yeah, so it's probably in there, and then I think the last point that I wanted to make, again, unfortunately, as I get older, I have these. Well, back in the day, we looked at these problems and went, nope, don't have compute power. Technically, we could model this, but it's better to build a test. I think what's changed is HPC. So the ability to model these multi-physics, multi-phase, multi-species simulations.
Right.
Now with massively parallel compute power being much larger, these are cost-effective simulations. Now you can actually do it faster and get better results than test in a practical way without being a national lab with the
Right.
supercomputer.
Yeah, with a whole room full of Cray computers to do it.
Exactly.
Yes.
No longer required. Yeah.
No longer required to do Crays. Yeah, I think back to my days when I first started doing this, and we had a Cray that
Mm-hmm.
would do the analysis, and it amazes me when I realized that Cray only had like 2 gigabytes of memory.
Right.
And that was a huge computer. That was a massive system. But nowadays, the hundreds of gigabytes is not. And we were modeling, a system that had 1 million cells.
Oh, wow.
And that was a big model.
Yeah.
And now on my desktop, I can model something with, 30 million cells without a problem.
Right. Without a problem. And if you do need that surge capacity, we're seeing cloud more and more. I know that some of our customers, some of our larger enterprise customers here at PADT, are using cloud solutions for HPC on their combustion modeling to get their emissions down, and doing these optimization studies and modeling modeling quite a bit more than they used to. Getting close with the 1D tool, 0D tool, 1D tool, and then some sector models, and then really optimizing on the full combustion model. So
right, and the other big thing is just that the scalability of the codes has gotten a lot better.
Yeah.
I mean, it used to be that 30 cores was kind of 60 cores. You started getting a drop off in the performance. Now I think the benchmark for Fluent is something in the order of tens of thousands of cores.
Wow.
And
those guys at the government labs, it's still linear.
Yeah. it's still a linear thing where adding more cores is a linear exchange in terms of the speed of the solution process. So it's the speed of communication, the efficiency of the parallelization of the codes. It's all, they've done a lot of work and it's all improved. So
interesting. Yeah, we could talk about that forever, but I think the big takeaway is what's changed over the years is multi-species, integrating chemical capabilities into the codes, as well as the multi-physics, which is becoming more and more important, because these are inherently multiple physics problems. And then yes, we can actually run it because of the improvements on performance and HPC. So it's definitely, hopefully you're thinking about doing this or things, and don't hesitate to reach out if you want to learn more about stepping into some of these more complicated and bigger analyses, and it or understand what that, maybe you're just thinking about it and want to understand what the payback on that is, what kind of numbers. And we talked about a few numbers that we can get up to 50% reduction in carbon emissions, was it on one? Yeah. I mean, this is not getting 2% fuel efficiency increase, which is still worthwhile doing. These are some big numbers. So if you need help understanding that, reach out to us, or whoever you get your answers from. Is there anything else Tom, you want to share with the audience before we wrap up?
No, I think we pretty much covered everything. I mean, the ability of the codes to handle, as you said, multi-species, multi-reactions, particulate matter. The one thing we haven't mentioned is the Rocky tool, which is
good point.
Another recent addition to the ANSYS suite of tools. And Rocky is basically a modeling tool for modeling large particulate matter and breakage processes. So if you're dealing with breaking up those large particles into smaller ones, or any kind of a process where you're mixing a fluid and a large number of particles.
Mm-hmm.
Rocky is very capable of doing that kind of work.
Okay. Because it's discrete particle modeling, right? And
right.
So,
it's a discrete particle modeling,
mm-hmm.
but it handles not just it handles the interaction of the particles with other particles
mm-hmm.
much
mm-hmm.
better than Fluent does by itself.
Excellent. I'm so glad you brought that up. I always forget about that, and it's a really cool tool as well. And my experience is we could probably mention a few tools in LS Dyna as well, because they always seem to have a module that can be applicable for something that you need to do that may be particle related, maybe fluid related, maybe multi-physics related, but highly transient.
Yes, LS Dyna does have those capabilities as well.
Yeah. So full spectrum there, which is really cool.
Yep.
And let's not forget our newest, well, not newest acquisition, but recent acquisition of Zmax. If you want to measure the particulate in the gas, modeling your sensor lens assembly is probably something you can do with Zmax, which we'll cover that some other time.
Yeah.
All right, Tom. I really appreciate it. Fascinating topic from both a physics standpoint and a making the world a better place standpoint. So really appreciate you taking the time. And we will hopefully talk soon about something else cool.
Yep. Sounds good.
All right. Talk to you later. Bye.
Bye.
So as you can see by listening in, I need to work on expanding my mind a bit on where and how simulation can play a role in this very vital area of engineering. It's not just about turbine engine combustion. I'm showing my background there. It seems like some big improvements are possible by combining multiple physics and species with various kinds of chemistry and high-performance computing to help get to the bottom line of the challenges that we're all facing. And they're going to get more challenging as time goes by. So please do go to brighttalk.com to watch Tom's talk on this and see some pictures, a little bit more detail on some things. That's our webinar on brighttalk.com. Just search for PADT. And as always, just feel free to reach out to us or whoever you get your answers from to try and understand how you can use this varied set of tools to lower emissions and improve efficiency and all that kind of stuff we talked about. So for today's commercial, let's talk about FlowNex. Tom just went through all the things ANSYS software can do, but we didn't really talk about the system-level thermal fluid tool that partners with ANSYS called FlowNex. If you need to model a system, maybe using the detailed simulation results we talked about, or co-simulation for components or subsystems, and then look at the entire system as a whole in transient form, FlowNex is your tool. If you are moving any type of fluids through something, FlowNex is the tool for you. We're seeing it used by our customers in turbo machinery to optimize combustion and improve secondary flow. They can do very quick what-if studies and get their combustion temperatures and chemistry and mixing better before they do a full fluids simulation. Also, various renewable energy systems that we work with are using to model and optimize their complex systems. And you can integrate your control software, your control algorithms right into the simulation, so you can do a lot of what-if there. We didn't really talk about using software to improve the efficiency of these processes as well. And you can model that using FlowNex. It's an amazingly powerful and easy-to-use system simulation tool that is the perfect complement to the ANSYS toolset. In fact, that's why PADT uses it for our consulting and sells it across North America. You can go to www.padtinc.com/FlowNex to learn a bit more, or reach out to us at products@padtinc.com, and one of our engineers can look at your needs and see how FlowNex can help. And yes, we do have academic and startup programs for FlowNex users. So please do reach out. Let us help you understand how this tool is a perfect complement and make your simulation even better. Taking a shift over to the news, ANSYS stock is sitting at $279.98 on Monday evening. That's May 2nd when I'm recording this. That's down just under 16%. I think it's 15.9% year to date. So not so great. The S&P 500 is down 7.7 year to date. Now, if you saw the headlines, but these were the worst 4 months since the Depression, I think, for the stock market. So tech stocks especially got hit hard, and ANSYS is in there. So we'll see how it goes over the long run here. I'm not going to dig in anymore. ANSYS is doing their Q1 number release on Wednesday of this week, the 4th, May 4th. Then, of course, they'll do their conference call, and we will be covering that in the next episode of this podcast, so you can learn more. The only ANSYS news I want to share is that ANSYS won a Gold Stevie Award. PADT, if you remember correctly, if you've been listening for a while, PADT won a Silver Stevie for our technical support team a couple years ago. And ANSYS has won a couple. And this latest Gold Award, which is for outstanding service in larger companies, they won for actually Simulation World 2021 event. So they won it for how good the event was. And it was a really good event. Want to know why? Well, the best way is to go to simulationworld.com and sign up for the 2022 event. It's coming up this month on May 18th. Highly recommend it. Lots of good, useful information about how to use simulation to make your products better. So it's not the technical deep dive into which key ops to use on an element or which turbulence model parameters to tweak. It's really about how to use simulation more effectively in your organization. So it's good stuff. It's very good stuff. Yeah, that's pretty much it for the news. Nothing else because they're doing the Q1 numbers. Of course, they're not going to really talk about anything. And then in PADT news, we don't have anything to share, but I don't have an excuse of releasing our Q1 numbers to Wall Street. We're just really, really busy and haven't had time to sit down and really think about what's new and news in our world. Things are going really well and customers are really happy. And hopefully we'll continue to just keep pressing forward and growing and doing great stuff. I will point out at this point that we still do have some job openings. We filled quite a few, but we've got a few left over both in the sales and technical support and engineering side. So if you're interested in either of those or know somebody that is, please do go to our website and check out the careers page. We go to About and then Careers. You can find it. What else? So the next thing to talk about is the ANSYS blog. Only really found two things to really mention in this one. There was some stuff that, I don't know, just didn't hit my fancy. You can check it out and see if there's something that you're excited about. But the one I wanted to point out is called Selecting the Right Battery for Your Application. Part 1, Important Battery Metrics. So if you're looking to put batteries into your device, car, vehicle, flying, whatever, submarine, how do you size those batteries? And it's a really good introduction to that. It talks about balancing, of course, energy and power and finding that sweet spot using ANSYS tools. This is part 1 on battery metrics. So there's more to come on how to select the right battery for your application. Really excited about it. This is pretty useful stuff, and we're all putting batteries and stuff, so it's useful. And then my second one is not really a blog post, but their podcast, Hover Cars and Hard Problems. The latest episode is called What Does the Future of Autonomous Cars Look Like? And they talk to some folks that are defining the future of autonomous vehicles. And it's a great podcast. Definitely check it out. Don't stop listening to our podcast, but do add the Hover Cars and Hard Problems into your subscription rotation so you can learn all sorts of cool things. They have some great customer stories on that podcast, and it's entertaining as heck to talk about ANSYS, as we know here. And that's all I have for blog articles. On the PADT side, we've got the latest is we got two kind of Flownex ANSYS related things. The blog post from our very own Miles Adkins is on Flownex 2022, and then also in our blog, and you can find it on YouTube as well. We have a link to a webinar we did with a company called ADT. They write software. They're an ANSYS partner that does software for turbo machinery design and simulation. And so we partnered with them to talk about Flownex, the ADT Turbo Design Suite, and of course the ANSYS tool set and how to use those to design better propulsion systems in less time and with greater accuracy. So it's a really practical look at how you can combine these tools together to get things done quickly. It's a great way to look at all three tools in a compact way. So do check that out. Again, that's in our blog, or you can go to YouTube and look for PADT INC as our channel and find it there. I only got one event after being a really busy April. This month is looking pretty mellow, which I'm very happy about. We've got a webinar called Mechanical Meshing Updates in ANSYS 2022 R1, which is going to be this Wednesday, the 4th. So do check that out on brighttalk.com or go to our website and see it on the events page. And that's it. I already talked about Simulation World, which is coming up as well. Definitely register for that. A few other local events here in Phoenix, but none of them are really simulation related. I'm going to be at the cybersecurity conference and some other stuff coming up, but probably none of you are going to be at that, so we'll just skip over that stuff. And I do want to point out that my partner Ray Chu, who's the true expert on all things 3D printing, will be at the Rapid TCT show coming up, as will our spin-out Oryx Additive. So, and there'll be other ANSYS people there, or PADT people there, and ANSYS will be there as well. So if you're interested in using the ANSYS tools to model simulation tools to model 3D printing, or you want to learn more about our post-processing from Oryx Additive, this is part post-processing, not result post-processing, do stop by either the ANSYS booth, we may have a couple folks in there as well, and at the Oryx booth. Those will be the two places that PADT people will be hanging out when they're not wandering around. So keep your eyes, if you're going to Rapid TCT, keep your eyes open for somebody in a PADT shirt. We'll have a few people there. So that's it. Don't forget to subscribe to our newsletter at padtinc.com/opt-in, and do spread the word. Subscribe to the podcast wherever you get your podcasts. And as always, don't hesitate to reach out. Thank you for joining us for the All Things ANSYS podcast, episode 110. As a reminder, this podcast is not affiliated in any way with ANSYS Inc., and the opinions expressed are those of the people on the show only, and not of their current or former employers. For more information, visit www.padtinc.com/blog, and please share your thoughts and questions through an email to podcast@padtinc.com. See you next time.